So I should start this video by mentioning I come from a physics background, and so I will be using examples from physics on the whole, but you shouldn't be afraid if you look at these equations and think, what are you talking about? I won't be relying on an intimate knowledge of the details of physical analysis, but I will be speaking in concepts that hopefully everybody will be able to understand. So there shouldn't be too much confusion. If there is, please comment, let me know. Would love feedback. But I think that this is a really cute demonstration of the way that I first understood complexity, at least. And it's a useful thing in establishing a perspective of where complexity kind of fits in a physics sense. Maybe not necessarily in terms of biology, which has always been dealing with complexity. But classical mechanics is kind of where physics first got its, walking legs. Ever since long ago, we have been doing, experiments with blocks and, spinning things, and how do we make arches stay upright. Things like this can be worked out relatively easily compared to some of the things that we do nowadays with computers. But oftentimes in classical mechanics, the systems that you're dealing with have very few components, number one, and number two, they're what we call weakly interacting. Now that just means that their interactions are pretty simple to understand and lay out. So I can use a single equation to say what's going to happen to this ball that's spinning around in my hand. So classical mechanics deals with very few things with very simple interactions. Now, earlier in the 20th century and a little bit of the 19th century, we started dealing with things that had way more particles. And we didn't necessarily know that things like gases and solids were all made of particles, but the idea is that in the study of statistical mechanics and thermodynamics, we can address systems that have just tons of particles, as opposed to classical mechanics where we can do maybe two. Statistical mechanics allows us to treat a room full of gas as a really simple object because all of the small, complicated interactions cancel each other out. This is why it's called statistical mechanics, because it deals mostly in probabilities and statistics. So what happens when we're in the middle here and we don't have so many particles that we can just average everything out, and we don't have so few particles that we can just understand the way they're interacting? You'll find actually that even in systems of maybe three things, you're in the middle here with complexity. So what we're going to try to do is show how things in complexity, and I'm going to make a quick plot here, and this is going to be a type of plot that I'm going to use in further videos. It's really just a visualization. It doesn't rely on any precise quantities. Like I said, we're going to be dealing more with qualities, but I just want to kind of plot what happens when we move from classical mechanics to statistical mechanics, because I find it's kind of interesting and it gives you a perspective of what's important in complexity. So I'm going to arbitrarily label this P and M, and I'll explain why in later videos. But let's just, for now, let's consider M to be the number of particles in our system. And let's consider P to be some abstract representation of the complexity of the problem. How rich are the dynamics that we can get out of this? And anytime I use a word like that, I just realize the term rich dynamics, that's something we use a lot in science, but if you want a better explanation of it, ask in the comments. It really just means, how interesting is this thing? How many different things can it do? That's a really watered down way to say it, but if you want me to explain further, please let me know. So, let's say I'm plotting complexity against particle number, okay? And every exact scientist in the room just cringed because there's no unit for complexity. But once again, robust qualities, not exact quantities. I'll explain later. Now, in classical mechanics, we have very few particles. and we're just going to say that it's not very complex. Nothing much is going on there. As you get to, you know, the three-body problem, which is, you know, three planets orbiting each other, you can get some very complex dynamics. And if you are interested in chaos theory, things can really get off the rails. But let's go over here. Now, in statistical mechanics, a good number to know is Avogadro's number. You're usually dealing with something like, 10 to the 24th particles in statistical mechanics. So I'm going to label this 1, 2, 3, ... And then we're going to talk about, you know, we'll say 10 to the 24th. That's a good number to go by. So here, tons of particles. Again, not a whole lot going on, but still worth some study. Now, what's happening in the ... What is going on here? In complexity, we see an interesting problem. See, in classical mechanics, there are only so many ways that you can arrange things. There are very simple situations that emerge from, you know, 1, 2, 3 objects. In statistical mechanics, the way that you arrange things is almost invariably irrelevant because there are so many different ways to arrange things, and they all, well, we assume that they all happen with equal probability, that you get very simple dynamics just because you have to go with the average. In complexity, the way that you arrange the elements of a complex system becomes incredibly important. And you see a lot more emergent phenomena, which is a word that I'm going to be dropping throughout these videos, because there are more physically significant arrangements that you can make, and they're more likely to occur than the likelihood that you'll deviate from the average in statistical mechanics. So this is what I'm going to be calling a PM plot, and you'll see that there, I'm ashamed, this marker sucks. So this is a PM plot, or so I'm calling it, and it's a heuristic device that's going to help us identify different ways that complexity emerges in certain problems. Yeah. So, if you have any questions, concerns, criticisms, I love criticism. Please criticize me. Let me know in the comments, email me, do whatever, just do something, otherwise I'm just going to talk to the camera. So, thank you for watching.